I'll be making the first video for the question 10 of probability and stochastic processes homework. First question, homework 10. So from the first part, I have to firstly explain what a Poisson process is. So for that, I'm going to refer to the notes as were provided in our lecture. So we see that the Poisson process, as it says, is basically a variable. It's a distributed random variable. And what this variable is used for is basically to tell us the number of occurrences of an event in a particular time event. So like over here we can see that it says the number of telephone calls. It can also be the number of buses that arrive in a certain term in time duration or anything. So it's basically the number of events happening in a fixed number of hours or minutes, or basically a duration. So this is the equation which has been written for the number of calls received, but we can actually use it for anything. It can be any event within a fixed time duration. What this is given by is actually e to the power minus lambda t into lambda t to the power k by k factorial. And in this entire thing, k is actually the number of times that event happens. Lambda is the variable. It's actually the parameter of the Poisson process, and t is the time duration in which the entire thing happens. So in this case, it says that lambda is the average rate. However, lambda is actually the parameter on which our entire Poisson process is based. Also, we know that the expected value of a Poisson process and also its variance, both these values are actually special values. They're always going to turn out to be lambda t, so they can be easily used in further cases. The next part is Poisson increments. So Poisson increments, as we can see from the notes, is basically a process that is defined on the existing Poisson process, in which we have a new parameter that's just entered, which is actually epsilon, that has to be greater than 0. So this has to be a given constant, and the new process, that's the Poisson increment process, can be defined as y of t is equal to x of t plus epsilon x of t. Over here is the Poisson process minus xt. So it's basically, if you see the difference of two Poisson processes which is separated by a time epsilon, and then of course that entire thing divided by epsilon. So we can see over here from the calculations that the mean, or eta, that's the expected value for y of t, that's the Poisson increment process, turns out to be lambda, just lambda. It does not include the t, because the t factor is cancelled out if you see by the epsilons. So as compared to the mean of a Poisson process, the mean of a Poisson increment is a constant lambda. It's nothing else. Nextly, we'll look at the autocorrelation function for Poisson increment process. So this is going to be the expected value of yt1, yt2. And when we try to calculate that further, what we get are these expressions. Excuse me. Now we'll be basically taking 4 cases in this, in which we vary the 4 time intervals, and that's t1 and t1 plus epsilon, t2, t2 plus epsilon, to make differences, whether they're independent or dependent, they're overlapping, and we end up with we end up with 4 solutions. And on combining all the 4 as itself, from combining from first to fourth, what we get is basically 2 general solutions, in which the first says that the autocorrelation value will be lambda square when the difference between t1 and t2, that's their magnitude, is greater than or equal to epsilon. And it's going to be lambda square plus lambda by epsilon minus lambda t1 minus t2 magnitude by epsilon square, when the magnitude is actually lesser than eta. So that gives us a graph over here, within which we see actually that the area of the shaded portion is eta, which is also actually the expected value and does not depend on epsilon, so it's a constant value. The third part that we'll be discussing is Poisson impulses. So what Poisson impulses is it's basically, again, just building up on the existing Poisson process. Over here we see that we're defining this new process, zt is a Poisson impulse process, and xt over here is our given Poisson process, the normal one. So what this is actually just, if you see the differential of this Poisson process. Now what this means, physically, in this case, yt is the Poisson increment. So it is the same thing as taking a Poisson increment when epsilon, that is the time that was going on, is tending to 0. So what essentially happens is when the time over here, when in a Poisson increment, when the time becomes very small, it goes down to 0. What we essentially get is just a pulse that's just going to exist on the point, and it's not going to exist even one millisecond ahead of the point, or anywhere except for the point. Is going to be 0. So it basically becomes an impulse as epsilon tends to 0. So we're going to find out the mean and the autocorrelation for this, and we know that the mean is going to be lambda, that's a constant, and the autocorrelation function is going to be the same thing that we found in Poisson increments, but just with an epsilon that's tending to 0. Just go back and show this. We know that the autocorrelation for the Poisson increment is lambda squared plus lambda by epsilon plus lambda t1 minus t2 magnitude by epsilon squared, and this, as we say that epsilon tends to 0, what we eventually get is lambda squared plus lambda and a del function with t1 minus t2. So it's going to exist, this second part is going to exist only when delta is at t1 minus t2, and it's not going to exist anywhere else. So anywhere else it's going to be just lambda squared, and besides that it's going to be lambda squared plus lambda. So the next part is finding out what a telegraph signal is. So basically telegraph signal has two parts. It's a random telegraph signal and a semi-random telegraph signal. So first of all, I'll be explaining what basically is a telegraph signal, and then we'll see upon what those two types, the semi-random and the random ones, are. So as we can see, a telegraph signal is basically, it's again, the basic concept for a telegraph signal is, yet again, it's a Poisson process, as we can see by the equation, because it's e to the power minus lambda t into lambda t to the power k by k factorial, which is the same as the equation for a random variable, which is a Poisson process. And we can see this, it says the same thing in the notes, that the underlying experiment is again the random selection of points with density lambda, and that is the probability of getting k points in O to t. So that's the same thing, the difference is t, that's why it's t over here, and the number of points is k, so it's k and k factorial, and the main parameter is lambda. So now basically, to explain what the two types, that's semi-random and random, are, semi-random telegraph signal has basically two values, it's either 1 or 0. Whereas if you have a random telegraph signal, it's gonna have just two values, that's a 1 or a minus 1. So in this figure that's been given, it's actually showing a random telegraph signal and not a semi-random one. So we saw, as we can read this, that at x naught, it's gonna be a fixed 1. So we'll say that if x naught comes out to be heads, it's gonna be 1. If it's gonna be tails, it's gonna be minus 1. So we have these two options, and it's gonna create a telegraph signal like this. So as we can see, it's defined as, it is going to be a 1 if the value of k turns out to be even in 0 to t. So if I'm tossing a coin, and if the number of heads is even, it's going to be a 1, and if it's odd, it's going to be a minus 1. So that's pretty simple. And if you see the probability mass functions, the expected value and autocorrelation function, what we get is that the probability mass function is going to turn out to be e to the power minus lambda t cos hyperbolic lambda t. The mean expected value is going to turn out to be e to the power minus 2 lambda t, and the autocorrelation is going to turn out to be e to the power minus 2 lambda into t2 minus t1. It's actually going to have a mod sign along with this, because it doesn't matter about the sign of the time differences around there. As we see that if you see a random telegraph signal, so we actually now have, we've taken that the probability of a being equal to 1 and minus 1 is equal as half. So if you try to solve and explain the random telegraph signal according to this, what we see is that yt is equal to axt, and when we try to find out the expected value for this, is going to be 0. The main reason is because the expected value of a is going to be 0. So when we're going to multiply these two things, it's going to be 0, because we just expanded them because they're independent. Similarly, the autocorrelation function, when we find it out, it's going to be ea squared rx t1 t2. That's the autocorrelation function for t1 t2. This is going to be 1. This is from the same thing as a semi-random telegraph signal. It's going to get us e to the power minus 2 lambda t1 minus t2 mod. So that mod is again showing that the sign of the time difference doesn't matter. So this is the random telegraph signal, and before it was the semi-random telegraph signal.